Hello, class. Today we're stepping into the shoes of roller coaster designers. Our mission is critical. Analyze a proposed roller coaster track segment modeled by a fifth-degree polynomial. Our main task is to find all the times t when the coaster car is exactly at ground level, meaning when h of t equals 0. In other words, we're finding all the zeros of the polynomial. This kind of task requires bridging the gap between the real world and mathematics. The use of real-world scenarios and problem-solving activities enhances understanding and motivation. Anomaly 2024. Think back to when we factored quadratics like x squared minus 4 equals 0. We factor it to break it down. We use that same concept here, but we start with the rational root theorem to list all possible zeros. Then we use synthetic division to test them. Testing roots is part of the working mathematically step of the modeling cycle. You won't always find a correct solution the first time in synthetic division. You might test 1 and -1 and find that they are not roots. Persistence is key. By repeatedly applying synthetic division, we successfully reduced the fifth-degree polynomial down to 3 linear factors and a quadratic factor, t squared minus 4t plus 1 after we factor out a negative. When solving rigorous problems, one strategy is to break that problem into segments. We now have our first 3 zeros, 2, -2, and 6. So now we focus on the remaining quadratic. Since the remaining quadratic t squared minus 4t plus 1 doesn't factor neatly, we use the quadratic formula. This gives us our final 2 zeros, approximately 0.27 and 3.73 seconds. We now have all 5 zeros. This whole process, from the initial problem to the algebraic solution, is known as mathematical modeling. We transition from mathematical results to real results. Each zero is a time the car hits the ground level, but we must apply the physical domain restriction, our section of track, from about 0 to 8 seconds. Since time cannot be negative for the ride, we should ignore our solution of t equals -2. The relevant ground crossings will be plotted as x-intercepts on our sketch. Also, the y-intercept h of 0 of -24 meters is visible from the standard form of our polynomial. This is reasonable in design if the track starts in a trench or the boarding platform is below ground. Visualization helps us understand the model. Because all factors appeared only once, every real zero has multiplicity 1, meaning the graph crosses the time axis at those points. Use end behavior to sketch the rest of the function. After substituting in valid points to find relative max and min, we can then get a better sketch of our roller coaster section. We see that the first peak reaches about 30 meters, a dip below ground near -30 meters, and a massive peak near 126 meters. We have reached the final and most critical stage of modeling. Validation. Our safety rules require the track to stay between -5 meters below ground and +12 meters above ground. Does our model comply? No. It drops 30 meters below the limit and peaks at 126 meters. Our mathematical results show this design is unsafe. We must reject the model. To fix it, we would need to adjust the function, like by applying a vertical scale factor between 0 and 1 to compress those peaks and valleys. This will tie back to your knowledge of function transformations. References are as follows.